Assalamualaikum and good day to all of you. We are still at chapter 4, higher order linear differential equations. In this lesson, we are going to discuss the first part of chapter 4.3, covering homogeneous linear equations with constant coefficients. Let us consider equation number 1, ay double prime plus by prime plus cy equals to 0. This equation is indeed of second order, and it is linear in y, where y is the dependent variable, and the gx is equal to 0, and that is the reason why we call this equation as a homogeneous equation, and we consider the coefficients a, b, c as constants. For example, a equals to 1, b is negative 1, and c is 3. So 1, negative 1, and 3, they are all constants. In general, we describe equation number 1 as a second-order linear homogeneous differential equation with constant coefficients. Since the dE is of second order, then there will be two solutions which we shall name them as y1 and y2. Let y1 and y2 be the two linearly independent solutions on an interval I. In chapter 4.1, we have learned that if the two functions y1 and y2 are linearly independent, and if they are solutions of the dE, then y1 and y2 form a fundamental set of solutions of the dE. Hence, we can write the general solution in the form of y equals to c1y1 plus c2y2. The question now is, how do we find the two solutions y1 and y2 for the equation ay double prime plus by prime plus cy equals to 0? To begin with, we are going to consider, or we're going to look at the special function which you are very familiar with, which is the exponential function, e to the mx, where m is a constant. Whenever we differentiate e to the mx, we find out that we'll get back the same function e to the mx multiplied by a constant. Y equals e to the mx, y prime is a constant times e to the mx. And y double prime will be another constant, m squared multiplied by e to the mx. In other words, the exponential function has derivatives as constant multiples of itself. Due to this, we assume that the solution of equation 1 is in the form of y equals e to the mx. Since we have said that y equals to e to the mx is the solution of this equation, that means y prime, y double prime must satisfy this equation. So let us substitute y prime and y double prime into the left hand side of this equation. So ay double prime plus by prime plus cy equal to 0. A multiplied by y double prime, which is given by m squared e to the mx, plus b multiplied by y prime, which is m e to the mx, plus c multiplied by y, which is e to the mx equal to 0. Notice that we have a common factor e to the mx among all these three terms. Since e to the mx is a common factor, we can factor it out, and leaving am squared plus bm plus c in this bracket. So now we have a product of two factors equals to 0. E to the mx is one factor, multiplied by another factor, am squared plus bm plus c equals to 0. Let us recall what we have learned in algebra. If ab equal to 0, it means that either one of them is 0 or both zeros. That is, either a equals to 0 or b equal to 0, or both a and b are zeros. Using this concept, we are going to understand how to solve this equation. This is a product of two factors, meaning that either e to the mx equal to 0 or am squared plus bm plus c equal to 0, or both are zeros. However, we know very well that e to the mx will never be 0. Since this is never 0, therefore am squared plus bm plus c has to be 0. So we have reached this equation which has a special name given to it. This equation am squared plus bm plus c equal to 0 is known as the auxiliary equation for the given differential equation. The auxiliary equation am squared plus bm plus c equal to 0 is a second degree auxiliary equation, where the highest degree of this equation is 2. Or we can call this as a second degree polynomial equation. Another name given to this second degree polynomial equation is quadratic equation. When we solve this quadratic equation, we will get two roots, which we shall call them as m1 and m2. Once we've obtained the values of m1 and m2, we can directly get the solutions for y1 and y2. Okay, in this slide, we are going to learn how to form the auxiliary equation. Auxiliary equation can be easily formed by simply replacing y double prime in the differential equation with m squared. Okay, y double prime, we replace it by m squared. Y prime with m, okay, replace y prime with m. And y with 1, y with 1. So, if the differential equation is 3y double prime minus y prime plus 2y equal to 0, the auxiliary equation will be 3m squared, okay, replace y double prime by m squared, minus y prime replaced by m, minus m, plus 2 times 1. Y has been replaced by 1. So, this is the auxiliary equation corresponding to the given differential equation. The auxiliary equation is of second degree, and therefore when you solve it, we'll get two roots, which we call them as m1 and m2. Now, how do we solve to get m1 and m2? There are various ways to get the answers for m1 and m2. We can use quadratic formula as given in equation number 5. m1 is negative b plus square root of b squared minus 4ac all over 2a, and m2 equals to negative b minus square root of b squared minus 4ac all over 2a. So this is the quadratic formula to find m1 and m2. Another method is by factorizing the quadratic equation if it is possible to factorize. Okay, so we factorize the quadratic equation to obtain the two roots, and we can also use calculator if it is possible to get the two roots m1 and m2. This is the general steps that we need to follow whenever we want to solve the differential equation in number 1. If you want to solve this equation ay double prime plus by prime plus cy equal to 0, the first step that you have to do is to form the auxiliary equation am squared plus bm plus c equal to 0. Once you've got the auxiliary equation, you solve this equation to get two roots, m1 and m2, and the m1 will lead us to the solution y1, and m2 will lead us to the solution y2. So once we've got the y1 and y2, we can form the general solution written in the form of y equals to c1 y1 plus c2 y2. In finding m1 and m2, there may be three cases that we have to consider. In the first case, what happens when the two roots m1 and m2 that we obtained are not equal to one another, and they are real numbers? Or in other words, we say the roots are real but not equal. m1 is not equal to m2. Now, if you use the quadratic formula, you will find out that this expression under the radical b squared minus 4ac is positive. In this case, if m1 is not equal to m2, then you will have to write the solution in these two forms. y1 is e to the power of m1x, y2 is e to the power of m2x. So these formulas are meant for solutions where the roots are real and distinct. In general, we can write down the solution y equals to c1 y1 plus c2 y2. So you plug in y1 into here and you plug in y2 into here, and that will be the general solution for case number 1. Case number 2 is when we have two roots and they are both equal. Okay, the roots are real and they are equal, and if you use the quadratic formula, you'll find out that the expression b squared minus 4ac under the radical is exactly equal to 0. So, since m1 is a real number, so we write the solution the same as in case number 1. y1 is e to the power of m1x. To get y2, since m2 is equal to m1, then we need to apply this formula, which is y2 is x multiplied by y1, or x multiplied by e to the power of m1x. So these are the two solutions, y1 and y2, and then you can write the general solution as given in this form. Case number 3 is when we have conjugate complex roots. If you use the quadratic formula, you'll find out that the expression b squared minus 4ac under the radical is less than 0. So the roots are complex. So we have here the root written as m1 equals to alpha plus I beta. This is the real part, this is the imaginary part. And m2 is alpha minus I beta. Again, we have the real part and the imaginary part. And m2 is said to be the conjugate of m1. What do you mean by conjugate? It means that the sign of the imaginary part differs from the sign of the imaginary part in m1. Okay, so if the sign here is plus for the imaginary part in m1, then the sign here will be negative for the imaginary part in m2. So when we encounter problems where we have two roots which are complex conjugate, then the solutions will be given as y1 equals e to the alpha x cos beta x, and y2 is e to the alpha x sin beta x. So this will be the general solution. Y equal to c1 y1 plus c2 y2. Let us look at some examples. The question is, find the general solution of the following second-order homogeneous linear differential equations. We begin by looking at this equation, y double prime minus 5y prime plus 6y equal to 0. So this is the auxiliary equation, m squared minus 5m plus 6 equal to 0. This equation is of second degree. You can use a calculator to get the answers. If you use a calculator, you will immediately get the answers 2 and 3. Or you can factorize, like what I'm doing, I'm factorizing this. You factorize m squared, you have m multiplied by m, give you m squared. And then you need to consider two numbers, which you multiply those two numbers, you get positive 6. And when you add those two numbers, you get negative 5. So in this case, the numbers are negative 2 and negative 3. Why do you choose negative 2 and negative 3? Because if you multiply negative 2 with negative 3, we get positive 6. And when we add negative 2 and negative 3, you get negative 5. So now we have a product of two factors equal to 0. Of course, you can also use a quadratic formula to get the two roots, m1 and m2. So if I use the quadratic formula, I'm applying the concept a times b equal to 0. Now we know that if a equal to 0, if m minus 2 equal to 0, then m must be 2. If b equal to 0, if m minus 3 equal to 0, then m equals to 3. So we get two roots, and they are both real numbers, and they are both not equal to one another. So we have a case of distinct real roots. Case number 1, m1 is not equal to m2. Now since the first root is a real number, so we look back at case number 1. Case number 1, if the root is a real number, the solution will be written as y1 equals e to the m1x. Okay, now you substitute m1 by 2, so y1 is equal to e to the power of 2x. The next root is m2, which is 3, also a real number, and therefore it will have the solution in the form of y2 equals e to the m2x. Substitute m2 by the number 3, so y2 is e to the power of 3x. So these are the two solutions, y1 and y2. Now we can form the general solution, y equal to c1 y1 plus c2 y2, or y equal to c1 e to the 2x, substitute y1 into here, plus c2 e to the power of 3x, this is your y2, substitute into here. So this is the general solution, for the given differential equation. Second question, y double prime plus y prime minus y equal to 0. Okay, let us form the auxiliary equation. Will be m squared plus m minus 1 equal to 0. This equation is of second degree. Now I cannot use a factorization technique here because you cannot factorize. This equation cannot be factorized. So I'll use quadratic formula instead. M is minus b plus minus square root of b squared minus 4ac all over 2a. Substitute, now we have a equals to 1, b equals to 1, and c is negative 1. Okay, a, b, c are all the coefficients of this equation. So a equals to 1, so substitute a by 1 into here. This is this one, 1. Substitute b equals to 1, so b equals to 1. B equal to 1, so 1 here, and lastly c is negative 1, substitute c by negative 1 into here. So you have negative b plus or minus square root of b squared minus 4 times a times c, or divided by 2 times a. Okay, now after we have simplified this function here, expression here, we get negative 1 plus or minus. Now 1 plus 4 is 5. So negative 1 plus or minus square root of 5 divided by 2. So notice that we have already obtained two roots. The first root where we consider the plus sign of the radical. The second root where we consider the negative sign of the radical. So m1 is minus 1 plus radical 5 or square root of 5 divided by 2. m2 is negative 1 minus square root of 5 divided by 2. These two roots are real numbers. They are real numbers and they are not equal to one another. So m1 is not equal to m2. So we say this is case number 1, distinct real roots. How do you write down the solutions? Since they are real roots, then we apply the formula for the solution if the root is real. y1 is e to the m1x. So substitute m1 into here. So e to the power of negative 1 plus square root of 5 divided by 2, everything multiplied by x. And y2 is e to the m2x. Okay, m2 is also a real number, so we apply the same formula for the solution for case number 1. So m2 is negative 1 minus square root of 5 over 2, so to place it into here. So now we got the solutions y1 and y2. You write down the general solution y equal to c1y1 plus c2y2. Third example, 4y double prime plus y prime equals to 0. The auxiliary equation is written in the form of 4m squared plus m equal to 0. In this part, you notice that m is a common number here. That's why we can factor the m. So factor the m. So we end up with m multiplied by 4m plus 1 equals to 0. Since now we have a product of two factors equal to 0, let us apply the concept a times b equal to 0, meaning m is equal to 0. This is m equal to 0, which I will label it as m1. Or 4m plus 1 equal to 0. 4m plus 1 equal to 0. Solving this, we'll get m equals to negative a quarter, which I shall call this as the second root m2. So m1, the first root is equal to 0. m2 is minus a quarter. 0 and negative a quarter, they are both real roots and they are not equal to one another. So we have a case of distinct real roots. Again, case number 1. So how do you write down the solutions for case number 1? The formula for the solution whenever the root is real is e to the m1x for y1. So substitute m1 by 0, e to the 0x is 1, so y1 is simply the number 1. Now y2 is e to the power of m2x. Again, we apply the same formula for the solution because this m2 is another real number. Now substitute m2 by negative a quarter, so y equals to e to the negative a quarter x. So these are the two solutions. Now we can form the general solution y equal to c1y1 plus c2y2, y equal to c1y1, now y1 is 1. So the first term is just a c1 plus c2 y2 and y2 is e to the negative a quarter x. The next question, d2y dx squared minus 10 dy dx plus 25y equals to 0. Auxiliary equation, m squared minus 10m plus 25. This equation can be factorized. Alright, so we get m minus 5 times m minus 5 equal to 0. We get the product of two factors equal to 0. Again, we are going to apply the concept a times b equal to 0, meaning that the first factor is equal to 0, the m minus 5 equal to 0, or the other factor is also equal to 0. We have another m minus 5 equal to 0. So we have two factors which are the same, m minus 5 and m minus 5. And either one of them or both of them equal to 0. So when we solve these equations, m1 is equal to 5 and m2 is equal to 5. Notice that these two roots are real numbers. m1 and m2 are real numbers and they are equal. So we are looking at case number 2, repeated real roots. m1 is the same as m2. So how do we write down the solution for case number 2, repeated real roots? Since m1 is a real number, whenever the root is a real number, the solution will always follow this form, y1 is e to the m1x. So substitute m1 by the number 5, so y1 is e to the power of 5x. To get y2, for case number 2, if the roots are real and they are equal with one another, then to get y2, you write y2 is equals to x multiplied by y1. Now, since y1 is e to the power of 5x, so y2 will be x times e to the power of 5x. So we get these two solutions, y1 and y2, and then you can write down the general solution, y equal to c1y1 plus c2y2. Another example, y double prime plus 18y prime plus 18y equal to 0. The auxiliary equation, m squared plus 18m plus 81 equals to 0. When we solve this equation, we get the product of two factors, m plus 9 equals to 0. So the first factor is equal to 0, m plus 9 equal to 0. And then we have another factor which is the same as the first factor, m plus 9 is equal to 0. In other words, we are getting two roots which are both equal to negative 9. So m1 is equal to m2. So we are looking at case number 2 again, repeated real roots. So y1 is e to the m1x and y2 will be x times y1, which is x e to the power of negative 9x. And this is the general solution. Before we discuss case number 3, which involves complex root and its conjugate, let us firstly understand what is a complex root and what is its conjugate. Complex root can be written in the form of a plus or minus bi. Okay, so a is the real part and b is the imaginary part and I is known as the imaginary number. And the rule for this is that I is equals to square root of negative 1. So when you see square root of negative 1, then we name it as I. And when you square the I, we get negative 1. Every complex root has its conjugate. In other words, if a plus bi is a complex root, then a minus bi is its conjugate. Okay, so the conjugate is formed by simply inverting the sign of the imaginary part of the complex root. What does this mean? Example, if 2 plus 3i is a complex root, then to get its conjugate, you simply change the sign of the imaginary part. So 2 minus 3i will be the conjugate for 2 plus 3i. Another example, if 3 minus 4i is a complex root, then its conjugate will be 3 plus 4i. We just change the sign of the imaginary part to get its conjugate. Another example, negative 4 plus 7i is a complex root, then its conjugate will be negative 4 minus 7i. So the conjugate, you obtain it by changing the sign of the imaginary part of the complex root, whereas the sign for the real part doesn't change. If it is negative, this will still be negative. And another example, negative 1 minus 2i, if it is a complex root, then its conjugate will be negative 1 plus 2i. You just change the sign of the imaginary part of the complex root to get its conjugate. Do not change the sign of the real part. Let us solve this equation, y double prime plus 2y prime plus 3y equals to 0. The auxiliary equation will be m squared plus 2m plus 3 equals to 0. This equation cannot be factorized. So if you use a calculator, you get approximate value. How to get exact value? It's important for us to learn how to get exact value for this auxiliary equation. To get the exact value, we have to use the quadratic formula. So m is negative b plus or minus square root of b squared minus 4ac all over 2a. So negative b is negative 2 plus or minus square root of b squared minus 4 times a, now a is 1, times c equals to 3 divided by 2 times a, again a equals to 1. Now simplify this, you'll get negative 1 plus or minus square root of 2i. Now how do we get that? Here's the work. Okay, so negative 2 plus or minus, now 4 minus 12 is negative 8. Square root of negative 8. Notice that we have a sign, a number which is less than 0 under the radical, so we expect that this root must be a complex root. Negative 2 plus or minus, now we know that negative 8 is 8 multiplied by negative 1. And we can split this into a product of two radicals or two square roots. It will become like this, square root of 8 multiplied by square root of negative 1. But we know that square root of negative 1 can be changed into I. So we get negative 2 plus or minus square root of 8 multiplied by I divided by 2. Now this square root of 8 can be further simplified into 2 square root of 2. Because square root of 8 is the same as square root of 4 multiplied by 2. Okay, now square root of 4 is 2. Because 4 is a perfect square. And then square root of 2. So 2 square root of 2. So negative 2 plus or minus 2 square root of 2i divided by 2. And after this, we take negative 2 divided by 2, which in that case we get negative 1, plus or minus 2 square root of 2i divided by 2. So this number to cancel. So plus or minus square root of 2i. So this is how I get this result. Now we get two answers. The first root is negative 1 plus square root of 2i, and the other root will be negative 1 minus square root of 2i. So this is a complex root, and this will be its conjugate. How do you write down the solution? For case number 3, whenever you have a complex root and its conjugate, you follow this formula. Y1 is e to the alpha x cos beta x, and y2, this should be y2, and y2 will be e to the alpha x sine beta x. So we just substitute alpha and beta into this formula. Okay, now what is the alpha, what is the beta? So let's look back at m1. m1 is negative 1 plus square root of 2i. Now the real part will be the alpha, and the imaginary part will be the beta. Okay, so alpha is negative 1 and beta is square root of 2. Now beta must be the same for both, and alpha must be the same for both. Okay, so we have y1 is e to the minus x plus alpha is negative 1 cos beta x, where beta is square root of 2, and y2, again sorry, this is y2, y2 is e to the negative x sine square root of 2x. Notice that complex root must always be in pair with its conjugate, and the solution are as follows. If one of them is in terms of cosine, the other must be in terms of sine. Cos and sine always come together, and the alpha must be the same for both, and the beta must be the same for both. Now we already got y1 and y2. We can write down the solution. Y1 is c1, y equal to, general solution is y equal to c1 y1 plus C2 Y2. Last question, y double prime plus 16y equal to 0. The auxiliary equation is m squared plus 16 equals to 0. Now we need to get two roots for this equation. Since there are only two terms on the left side of this equation, and one of the terms has no m at all, and this is of second degree, then we are allowed to shift the 16 to the right side to get the solution. So we write m squared equals to negative 16. After this, we are going to find m by finding out the radical or the square root of negative 16. So m will be plus or minus square root of negative 16. But we know that negative 16 is the same as 16 multiplied by negative 1. And then we already know that we can split this into a product of two radicals. That will be square root of 16 multiplied by square root of negative 1. Now keep in mind there is still the plus or minus sign written here. Now square root of 16 is 4. So because 16 is a perfect square, 4 multiplied by itself gives you 16, and square root of negative 1, we define it as I. So we have two roots, 4i and negative 4i. So this is a complex conjugate roots, case number 3. So how do you write down the solutions? We are going to follow this formula when we have complex conjugate roots, e to the alpha x cos beta x for y1, and again, sorry, this should be y2. y2 is e to the alpha x sine beta x. Okay, what you have to do is to substitute alpha and beta into this formula. Let us identify the values of alpha and beta. Okay, m1 is 4i, m2 is negative 4i. 4i is the same as 0 plus 4i. That means the real part or alpha is 0 and the beta is 4. m2 is minus 4i, that is 0 minus 4i. Again, the real part is alpha, which is 0, and the imaginary part is beta, which is 4. So substitute 0 alpha equal to 0 and beta equals to 4 into these formulas of the solutions. So you get e to the 0x cos 4x, by e to the 0x is 1, 1 times cos 4x is cos 4x, and then followed by y2, e to the 0x sin 4x, e to the 0x is 1, 1 times sin 4x is sin 4x. So now you can write down the general solution, y equal to c1y1 plus c2y2. Thank you.